All right, ladies and gentlemen, welcome back to chapter two. This is our first set of actual notes, and we are going to be focusing on the properties of water. And we're going to be talking about the food involved in your body's chemistry in a different set of notes. So today, just talking about water itself. And we're going to be revisiting a couple of vocab words. So this should be easy if you paid attention in the last video. Cohesion. Your keystone definition is an intermolecular attraction between like molecules, meaning two of the same kind of molecules are going to stick to each other. Example, water molecules will stick to water molecules. As the water is pouring out of this glass, instead of coming out as a whole bunch of droplets, it's coming out as one long stream. All the water molecules are holding on to each other. As you can see, when one drop of water meets another drop of water, the molecules join together and become one larger drop of water. And not only that, but when I try to get this other drop in there, instead of flowing into it, it continues flowing into itself and won't join. This is important for you because this is how your blood works. Your blood is made of water, and this cohesion allows it to work as one flowing unit. This is going to cause what we call surface tension, or in other words, the reason why belly flops hurt. All right, that has that little layer of slightly thicker water at the top of the pool or the top of a glass of water. Taking a look at my example here, this is my very artistically drawn diver of science. He's going to jump into this pool, but we want to focus not on him, but on this section of water. Let's zoom in. And all these little circles represent water molecules. I know it's so super accurate, right? Very scientific over here. But the idea is these water molecules are trying to stick to each other. Not only is this guy pulling on this and this guy is pulling on this and they should be coming together, but this guy is also being pulled to this one and this one and this one. They're being pulled in every direction. It's like tug of war, so they really can't move too well. And that's happening all over the pool. It's happening in every direction. These water molecules are being pulled in every which way, so they're not really moving, except at the top. Take a look at the top. These water molecules up here are being pulled side to side. Sure, they're being pulled down, but they're not being pulled up. There's nothing up here. So these water molecules have a whole bunch of downward pull, and they're being squished into the next layer of water molecules, making this top section much thicker. And you can see this for yourself. If you ever take a look at a glass of water, at the top, you can see a slightly thicker line where the water molecules are more densely packed together. That is cohesion. The cohesion of the surface of the water creates a layer of resistance. We call that surface tension. It also has a different name. It's called the meniscus, which is not a word you're going to hear too often. I just thought you'd be interested. And like I said earlier, it is the reason why belly flops hurt, because water will move out of the way when you hit it, but that meniscus is thicker and it's slower. It doesn't get out of your way quite as fast. So the faster you are going, more it's going to hurt. Try jumping out of a plane and it feels like hitting a brick wall. Why is cohesion important? I mean, this sounds like chemistry, not biology. That's because biology is chemistry, right? It is actually a whole bunch of chemical reactions that's keeping you alive. So one of the reasons why cohesion is important, in this case for us, your blood. Your blood is constantly moving all around your body, and you don't want any gaps in your blood. Your blood is made out of water. So all that cohesion is keeping your blood together. So instead of having a whole bunch of droplets floating around, you have one steady supply of one connected bloodstream. Another reason why it's important is because our metabolism needs a watery environment. Chemistry doesn't really happen unless it's in water, at least not the chemistry that keeps us alive. So in order for all of our chemical reactions to be where they need to be, they need to travel through our blood. So we need to get one solid supply so they can move. If it was a whole bunch of droplets, then all the chemicals would be stuck in individual droplets and they couldn't react. Adhesion is similar but different than cohesion, right? It's still stickiness, but it's not sticking to itself. Adhesion is the intermolecular attraction between unlike molecules. Example, water sticking to your hair. Right? Instead of water sticking to itself, it's sticking to you. Another example is water likes to stick to the ceiling. When the pipes in the ceiling start dripping, instead of dripping through the ceiling and landing on you, water just gets stuck in the ceiling tiles and builds up. And then you can also see in this picture, it's getting darker, right? It's not just wet, but dark. That's because dust is adhering to the water and it's getting dirtier and dirtier. And then, water droplets adhere to spider webs. So you can actually see spider webs a lot easier after it rains. This is a beaker or a test tube. Water likes to stick to the glass on the inside of the test tube. That right there is what we call capillary action. That was the vocab word where things climbed up a tube. A tendency for water to rise up a thin tube. As we said in the vocab, the water, in this case, is going to climb up the inside of this tube because it's sticking to the inside of the tube. And it keeps rising and rising, causing it to defy gravity. Right? The adhesiveness or the stickiness of it is stronger than gravity is pulling it down. So it's going to start rising up. This also works with paper towels. It's a much easier example. All right. Why is capillary action important for us? It is important for life in general. Yes, I said earlier in the vocab that capillary action is going to help it go through your bloodstream, but much more important, capillary action is going to help plants get at water, because you can just drink water by tipping it down your throat and swallowing. Plants don't have those muscles. So they just sit in the dirt and water will rise itself up the plant's roots. When it gets to the top, the plant basically sweats, but we don't call it sweating for plants. We call it transpiration. When humans do it, it's perspiration. When plants do it, it's called transpiration. All the water molecules that they're done using turn to a gas and evaporate away. Helps cool the plant down. So how are we going to tell the difference between cohesion and adhesion when looking at it? When in cohesion, the surface tension tries to make a ball. That's because all of these water molecules are sticking to each other instead of the surface around here. So they end up trying to pull in on each other, pile up, and they end up making a little bubble. And you can actually look at the side of it and see that there is water hanging off the edge. There's like a gap. It's defying gravity here because it's pulling on itself and lifting up. Where adhesion, water sticks to something else. In this case, the water wants to stick to whatever this surface is, and all those molecules are trying to flatten out so it can spread. So cohesion will bubble up, adhesion will stick to whatever it's touching. With that in mind, take a look at these two test tubes. One is full of water, one is full of mercury. Question, and I will answer it for you, but I'll give you a second to think. Which test tube shows cohesion and which test tube shows adhesion? I'll give you a few seconds to think about this. All right, so if you said the cohesion was being found in mercury, you were right, which means adhesion is in the water. Whoops, why is that? Because we said before, cohesion, the molecules are sticking to themselves, so they're piling up on top of each other and made a bubble. Over here, adhesion, the water is trying to stick to the glass and it's starting to climb up the side, so it's kind of rising up on the edges. Important thing, more so for chemistry class, I get a lot of people taking chemistry and biology at the same time. So if you're in chemistry class, guys, there's something you got to be aware of, because some things are more cohesive, some things are more adhesive. You can get false measurements So what you want to do is never measure off the side that could be climbing or dipping down. You want to measure from the middle every single time. That's how you're going to get your accurate measurements. Changing gears, high specific heat, the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. What does that even mean? That means it takes a lot of energy to warm up water. That's what high specific heat means. Let's think of something with a low specific heat, a paper clip. Right? If I were to put a paper clip over a lit match, that paper clip would get hot very quickly. It doesn't take a lot of heat from that match to make the paper clip hot. However, if I were to put that same match under a small glass of water, then that water will just keep absorbing the heat, absorbing without actually getting warmer. It would take a tremendous amount of heat from that fire to raise this glass's temperature from 20 degrees Celsius to 21 degrees Celsius. That's high specific heat. How much heat does it take? How much energy does it take to warm up this glass of water? And like I said, for water, it takes a lot of energy, more than any common substance. Like I said, water is weird. It takes a lot to heat it up. So why is that important for life? Again, that doesn't sound like biology, because we need Earth to be a livable temperature. Think of Venus. Yeah, I know, different planet altogether. You probably are picturing it. It's right next door to us, all right? And it does not have water on the planet. So it gets very, very, very hot on that planet. On Earth, though, we do have water. So all of that sunlight that should be cooking us, instead of heating us up, it goes into the water, and the water absorbs it without actually getting warmer. This cold water stays cold, despite the fact that the sun is heating up. I mean, it gets a little warmer, but not as hot as you think it would. And cooler water keeps the air cool. So we stay cool and we're happy. And here's the cool thing, at night, without the sun, guys, we should be like the Arctic tundra all over. Like, we should be freezing to death every night, but we don't, because all of that heat from the day stays in the water, and that warmth is there to warm up the air and keep us at livable temperatures at night. Without water, we would have the two extremes. We would be a fiery death ball every afternoon and a frozen wasteland every night. This water keeps it at livable temperatures. Changing gears again, this was not a vocab word, but still important. Water is known as a versatile solvent or a universal solvent. What that means is it dissolves things. Solvents dissolve things, and almost anything can be dissolved by water. It's not a very strong solvent, so it can take a very long time for some things, but maybe not even your lifetime. But everything will get broken down by water somehow, some way. And that's very important, because the things that get dissolved become those very small molecules we talked about in vocab, and that's where chemistry happens, with those broken down molecules. pH scale. Acid, pH of 7 to 0. Base, the pH of 7 to 14. Water is right in the middle at a 7. I talked all about this in greater detail in the vocab, so I'm not going to go into too much detail about it right now, but basically, pH, which means potential for hydrogen, is how much hydrogen is in this liquid. The more hydrogen there is, oddly enough, the smaller the number is. I don't know why they did it that way, but the smaller the number, the more hydrogen, which means the more acidic it is. And then the less hydrogen, the larger the number, the more alkaline or more base it is. The stronger in this one direction, the more acidic it is, the more dangerous. And then the stronger in this direction, the more dangerous. So somewhere right in the middle is not dangerous. And 7, perfectly in the middle, perfectly neutral, not acid or base, is water. So what is a buffer? A buffer is a weak acid that weakens a strong base, or it's a weak base that weakens a strong acid. Basically, if you were to spill hydrochloric acid, this is the example I gave in vocab. If you were to spill hydrochloric acid on the floor, you can take something that is this weak base, add it to it, and that will weaken the acid, make it safer to handle. Again, why is that important for biology? Because your body is full of chemicals, some of which are acids, some of which are bases, and buffers can be kinds of medicine. For instance, your stomach is full of hydrochloric acid, very dangerous stuff if it's outside your stomach. And if you start getting sick, the doctor may tell you to go get some buffer. You can actually get it over the counter without a doctor's permission. It's called Tums. Tums are a buffer. Pepto-Bismol is also a buffer. It calms down the acid in your stomach. Water, I wrote this weird. I wrote that water is a weak acid and a weak base. What I meant to say is it acts like that. Right? It's not acid or base, but if you were to put water into an acid, it would act like a weak base. It would be a buffer. If you were to put it in a base, it would act like a weak acid. It's going to act like a buffer for both of them. It's not a very strong buffer. It's not a very good buffer, but if you don't know what you're handling, water is the safest one to use. So it will do both. Again, why is that important for life other than your stomach acid thing? Also, it's going to affect the chemistry in your body. The example I have here is building a blood clot, you may know as a scab, right? It takes certain chemical environments for a scab to form. If your pH is weird, you may not make that scab and you can bleed to death. So you can actually use a buffer to calm that pH down and allow your body to work properly again. So if your pH isn't balanced, you can get very, very sick. And as I said over here, a pH imbalance can affect the activity of enzymes that clot your blood. In fact, messed up pH can mess up all of your enzymes, which we said in the vocab, very important. And the last thing we're going to talk about is density of water. Most things, this is actually one of the weirdest things I think about water. See, most things, when they freeze, they get denser, meaning all the molecules start coming closer and closer and closer together. It becomes thicker. But for water, they actually get spread apart. They actually become less dense when they freeze, meaning less dense things are going to float. Oh, that's going to be important later. I'll come back to that. So when water freezes, its molecules make up a hexagonal shape. Like I said, most things, the molecules get closer and closer together, but the way water molecules look, they actually connect to each other like puzzle pieces almost, and make these very specific shapes with all these hollow, empty gaps in between. They're spreading them out, making them lighter, making them less dense. So why is that important for life? Because very, very, very dense things will sink in water. When it's less dense, it will float in water. All this ice floating on the top will protect this fish from the cold, harsh winds and knocking tree branches down, things like that. This fish is safe. But if water got denser, that ice would sink and that poor fish would get crushed. All right, guys, that is it for the notes. Please go and check Power School or check Google Classroom and see if there's an assignment waiting for you. Good luck, guys.